Hello! Welcome to Physics Lesson 5.4, Forces in Two Dimensions. I spent a whole bunch of time trying to figure out how to reduce this lag and make it, stop being choppy. Trying to figure it out. So, you're stuck with super choppy. But anyways, dimensions. So, we've already kind of talked about this a little bit, but essentially what we have is you can have a force going up and down. You can have a force going this way and this way. Now we're going to include having a force that goes perpendicular to itself here. So let's see how this plays out. Let's do this elevator one first. So we have Roy. He's very massive. He's sitting on an elevator. He's sitting in an elevator. He's got a bathroom scale which measures weight in newtons, not pounds. Good, so I don't have to convert. What is the force of gravity? So here's our elevator. Boop, 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 boop. Here's Roy. Alright. He's sitting on the scale. Let's find out our force of gravity. So force of gravity, 70 times negative 10. That's supposed to be times. Meters per second squared. That should give us negative 700 newtons. Yeah, look at that. So Roy weighs 700 newtons, right? Force of gravity, 700 newtons going down. Good. The elevator travels up. Let's put this down in here first. Oh, there it travels up, and the scale now reads 2,000. What the heck is going on with Roy? So what that means is that our normal force up here, equals 2,000. What force is the scale measuring? Well, that's our normal force. What is the net force acting on Roy? Well, force net equals 2,000 newtons plus a negative 700 newtons. So our force net is 1,300 newtons. And they're traveling up, which makes sense. This is positive. Sweet, not T, positive. Alright. Next example, we have a physics book. It moves forward on a friction-full surface. Draw a free body diagram. So this dot represents our book. Force of gravity pulls down. Label that weight so we get used to using that term. But it's not falling through, so we have normal over here. Those two should be equal, otherwise it would move up and down like in our elevator problem like before. But this is a friction full surface, which means that we have friction. Friction is going to go against whatever we are trying to do, and it's moving forward, so it's trying to go that way. These two should be equal as long as it's at a constant velocity. Woo-hoo. Anyways, okie dokie artichoke. If the normal force keeping the book on the surface is 100 newtons, how massive is the book? Well, what we just said is that this is 100 newtons. Yay! And it's equal to the weight, only in the opposite direction. So, negative 100 newtons, right? So that they add together, balance out. That should equal our mass, which is what we're looking for, times the acceleration of gravity. You guessed it, it's negative 10 meters per second squared. So the mass of our book is 10 kilograms. If a force of 50 newtons is applied to the book, but the book only accelerates to the left at 4 meters per second squared, how much then is the force of friction? So let's draw this out. Maybe not. There we go. Square. Boom. We still have the force of gravity. That's still going down. Yay. We still have normal force going up. Those should balance each other out. But now what we're saying is we have this force being applied to the book, and it's moving to the left. There we go. And since it's going left, that's negative 50 newtons. We are looking for our force of friction, right? And our force of friction should be going in the opposite direction of what we're moving at. So let's figure that out. First, what I like to do is figure out our force net. So what is our total force, with our total mass and our total acceleration? So our total mass is 10 kilograms, same book. Our acceleration is -4 meters per second squared, right, to the left. So our net force should equal -40 newtons. But it's only moving, there's negative, I can't talk today. Oh my goodness. All right, so -50 newtons is going to the left, but it's only moving with a force of -40 newtons, so something is taken away from that. So -40 newtons equals -50, the force we applied, plus friction. So friction is +10 newtons. All right, last one. We have a box. It's moving along a frictionless surface. Here is our box, and what we now have is forces that are perpendicular to one another and in a 90-degree fashion. That's a really bad 90-degree angle. I apologize, but what is the resultant force? So in order to figure that out, what we need to do is do a little bit Pythagorean theorem. So you might notice this as a squared plus b squared equals c squared, right? The force here. And that should give us this force right here. So what it's moving at. And that should be, so 500 squared plus 250 squared should give us our c squared. Then we got to take the square root of that. Yay! And we should end up with force equals 559 newtons in the southwest direction, or west of south, whatever you prefer. If the box has a mass of 50 kilograms, what is the acceleration? Well, now that we know that it's 559 newtons as a net force, it should equal 50 kilograms times whatever our acceleration is what we're looking for. So acceleration should be 11.2 meters per second squared. Draw a free body diagram of the net force acting on the box. Sure. Free body diagram. Boop, boop. Yeah, let's do a nice arrow. I'll do purple. I like purple. Alright. Should be going that way, right? And that is the resultant vector of these two component vectors. Oh, see what I did there? Alright. Yeah, fun times. Life is good.